Hello, Marek.
Hi,
So,
hello.
Marek is a PhD student from Poznań University of Technology and works as a data scientist in OLX Group. The topic of his presentation is extreme classification, applications, and algorithms. And this explains, Marek focuses mostly on extreme classification, but maybe he will talk more about it instead of me. And I was supposed to remind you that you should ask questions in the Q&A section, but I see that you did this, so no problem. And let's start with your presentation.
Okay, thank you, Michał, for the nice introduction. And again, hello, ladies and gentlemen. So today I would like to shortly introduce you to extreme classification. This is quite a new field in machine learning, which I think gained momentum in the last 2 years due to some recent advances that actually bring promise that extreme classification can be used successfully applied in wide spectrum of key industrial applications. So my today's presentation is divided into the following parts, since some of you might not have heard the term extreme classification. I will start by giving you some context of the field. Then I will discuss a wide range of applications considered by the community. I will try to show you that many AI problems can be naturally modeled as extreme classification. Next, I will briefly tell you about the landscape of state-of-the-art solutions. And due to the time constraints, I will focus on one particular family. And I also have a good reason for that, since this family is implemented in our recently published library, napkinXC, one of the first that allows to easily apply extreme classification using just Python library, using just Python and few lines of code. Yeah. So in the field of extreme classification, we are considering two classical machine learning problems. The first one is multi-class classification, where the aim of the classifier is to classify each input into one of the several possible target classes. And the second one is multi-label classification, where the aim is to classify each input into multiple categories. Like, in other words, assign a subset of relevant labels to the data point, and the number of relevant labels can vary from 0 to the maximum number, to all possible labels. So note that multi-class classification is a special case of multi-label classification, when each example has always only one label. So these are a pair of classical machine learning problems. However, with the advent of big data era, we can easily find learning problems with very large number of classes or labels, reaching order of hundreds of thousands of, or even millions of labels. And we refer to those problems as extreme classification. So it is generally agreed that extreme classification is just multi-class or multi-label problem with a number of labels that is larger than 10 to the fifth. And also the number of features and number of examples is also often very large, larger than 10 to the fifth. But potentially it can be much, much larger. So shortly, it's very high dimensional setting. Additionally, in case of multi-label setting, it's usually assumed that the number of positive labels is on average much smaller than the number of all possible labels. Yeah, so this is problematic, because if we apply the most straightforward approach, which is one versus all with linear models, the train time complexity will reach the order of number of labels times number of examples times number of features, which will be very large. So even with modern hardware, GPU acceleration, large problems of such scale may not be possible to solve using this naive approach. So one of the main challenges of the extreme classification is to develop algorithms with time complexity below linear in terms of the number of labels. And the first and most obvious example of application with such large number of dimensions is categorization of text and articles. For example, assigning categories for new Wikipedia articles. The English version of Wikipedia currently has over 2 million different categories. On the slide, you can see a set of categories assigned to the article about Alan Turing. So as you can see, it's really vast and diverse. And so in this case, you can really easily frame it as an extreme classification problem. The text corresponds to features, and relevant categories serve as labels. Another similar example could be a prediction of topics, hashtags for posts in social network, where feature space expands from text domain to image and maybe even video. And we treat hashtags as our labels. And we can use this to improve our post multimedia search possibilities, as well as this can help us to better understand our content if we will be able to assign labels to untagged, like hashtags to untagged content. And while we are around the search, one of the first applications of extreme classification was reported by Microsoft Research in 2013. They used a multi-label random forest classifier to predict for any ad Bing queries that might lead to a click on this ad. And according to the paper, this approach outperformed significantly NLP and information retrieval techniques implemented back then in Bing. As far as I know, they continue to use extreme classification approach in the Bing search. So here, of course, the ad and its content serve as the features, and different queries from our search engine that was clicked that lead to the click on the ad can serve as a labels. And we can go even a bit further. So recently, a team from Amazon successfully tested using the extreme classification model as a way of proposing relevant items given a search query. So we can basically say that they replaced the search engine with classification model. In this case, such search query plus optional context, like for example, some user features, like I basically serve as the features, and relevant items are labels. And those labels can be presented as a list ordered by a score returned by an extreme classifier. So it's worth noting that on platforms like Amazon, AliExpress, Alibaba, we have millions of those possible items that we can return. And we can also go back to the other core problems of machine learning and reformulate them as extreme classification tasks. And I'm thinking about item to item user recommendation. And the way we can make it work is to treat each label as separate item that can be recommended. And also the same items can be treated as the features. So in case of user to like item user recommendation, you can basically treat the user history. So items it clicked bought as a features and try to predict clicks or some other actions that will happen in the future. In case of item recommendation, item-to-item recommendation is easier. Basically, we can use item features to predict other relevant items. And again, depending on the application, labels can be recommended as a set or as a ranked list sorted by some score predicted by extreme classifier. And it's not the end of possible applications. There are many other problems that can be easily formulated into this framework of multi-class, multi-label classification. A lot of problems in computer vision, like person or landmarks recognition on photos, natural language processing, and many others. So I hope that at this point you notice that many problems can be naturally modeled as extreme classification. And now the question is why we would like to consider extreme classification as a solution for many of those mentioned problems, applications. Because actually we already have solutions for many of those. And I will be generalizing a lot now, but I think I can state that embedding models are currently state of the art and serve as the backbone for many of the like behind the solutions for many of mentioned problems, especially in the area of recommendation and information retrieval. And for those who didn't see Piotr Bojanowski's keynote, embedding models relies on projecting the inputs and outputs onto a small dimensional subspace in which relevant entities should end up close to each other. But they often have a major bottleneck. The optimization is based on pairwise loss function that leads to a huge number of training instances. Each input label pair is a training instance. Also, negative sampling that is often used on those models adds to the problem. I would also add that they have many hyperparameters, often have many hyperparameters related to the loss, to the negative sampling, etc., that require tuning. So using extreme classification approach may be actually faster, more straightforward, and maybe even better performing. Yeah. So okay. So I guess now it's finally time to say a bit how we can tackle those extreme classification problems. The landscape of the state-of-the-art solution for extreme classification is, I would say, vast at the end of 2020. We have a lot of families of algorithms. We have the first one is a group of smart linear one versus all approaches, with the most known are DSMEC and PPD sparse. Those requires a lot of resources to train and predict, but in general perform very well. We have a family of ensembles of huge number of decision trees, where the fastXML is the best known example. There are approaches based on approximate KNN, like AMLC, and of course we have some deep learning methods. But there is also one more family that is recently very popular and successful in solving extreme classification problems. A group of labels trees, in particular the probabilistic label trees, that were recently implemented in several state-of-the-art algorithms like Parabel, Extreme Text, or Attention XML, and in few others that are not listed here. So let's dive into the idea behind probabilistic label trees. And first, let me introduce some additional notation. With every data point, there is associated a subset of positive labels. And this set of labels is identified with a data point labels vector in such a way that if the value at index j in the vector is equal to 1, then the label small lj is in the set of the positive labels. And now we can go back to probabilistic label trees, PLTs in short. And PLTs reduce the original multi-label problem to a set of binary problems organized in the form of a tree, in which each leaf corresponds to one and only one label, and the paths from the tree root to leaves factorize marginal probability of label using a chain rule. So to clarify, the label's conditional probability is equal to the probabilities product estimated in all the nodes on the path from the root to the label leaf. So every node in the tree estimates a probability that at least one label in its subtree is positive, given that at least one label is positive in its parent subtree. And it's starting from a root node that estimates the probability of any label in the tree being positive, since in the case of multi-label classification, an example can have also 0 positive labels. Yeah, so I prepared this toy example to show you the process of learning such a tree. I will go through those 4 data points, each with a unique label, and mark with the filled dots nodes that need to be updated positively for that example, and with empty dot nodes that needs to be updated negatively. So as you can see, due to conditional formulation, not all of the nodes needs to be updated for every example. Only nodes on the paths from positive labels to root and their siblings needs to be updated, resulting in logarithmic training time in case of balanced tree. So basically, number of examples in the lower nodes that lower nodes needs to learn will be much, much lower than the number of all examples. So that's that's why these labels trees are very efficient to actually train. But then, when it comes to prediction, we can apply different algorithms depending on our application and measure we'd like to optimize. We can use a uniform cost search. It means that starting from the root node, we search a tree and evaluate. We always pick the next unvisited node to evaluate that has the highest estimated probability so far. So this approach in the worst case will work in a linear time, but in practice, its performance is close to logarithmic. But we can also use a beam search strategy, which also search a tree starting from the root node, but only keeps a list of some n best nodes at each level of the tree, and it guarantees logarithmic prediction time. So this kind of trees also allows for efficient prediction of labels with the probability above the given threshold. And what really distinguish PLT from many other extreme classification methods is the fact that it's really a general framework that does not impose restrictions on node estimators or future representations you can use with it. So that's why that's why we see it successfully applied as part of different, much more complex architectures that achieve state-of-the-art results. But the problem with PLT and other extreme classification algorithms is the fact that they are not easy to implement efficiently in high-level languages like Python. And right now, we lack easy-to-use extreme classification software and libraries that developer can just pick up to test if it works for her problem. So that's why we recently decided to polish and publish the napkinXC library that previously served as our experimental platform. And napkinXC is a simple and fast library for extreme multi-class and multi-level classification for Python, but with extremely efficient C++ backend. And it implements a SOTA version of PLT and a few other algorithms, and allows you to train a classifier for very large data sets in just a few lines of code with minimal resources. And supports NumPy and SciPy data types. You can easily install it using PyPy, and implements different types of predictions that you can actually select based on your applications. And currently, it supports only PLTs with linear models, but we are working hard on enabling usage of custom models, including like deep neural architectures. Yeah, and now I want to show you some results on extreme classification. No, I don't. Actually, I could show you some results on extreme classification benchmarks right now, but instead I decided to do something else for this presentation. So this week I obtained some results on the popular recommendation benchmarks using our napkin library. So here is a comparison of napkin's implementation of PLT with two other very popular recommendation algorithms, YouTube DNN and LightFM, on two very popular data sets, MovieLens and Amazon Books data sets. And as you can see, PLT outperforms significantly both of these. And I will also add the note that I just use the PLT with the default parameters in our library, while for other two algorithms, I need to use actually 50 rounds of random search to find a good parameters to achieve those results. So this is very small demonstration, but I think it somehow shows that extreme classification may be a promising solution also to other problems than just simple classification. So yeah, so I think that's all from my side today. So summarizing, many AI problems can be naturally modeled as extreme classification. Probabilistic label trees are a successful approach to extreme classification, and it can be easily applied thanks to our implementation napkinXC library. And you can find the library on GitHub. Also, if you want to know more about PLTs, we recently published very detailed publications on them. So you can also see a link to archive on this slide. Yeah, so that's all. Thank you for your attention, and I will gladly answer some questions.